We are discussing the topic of concurrency control, and in that topic we have seen that the major issues are maintaining the consistency of shared data access during concurrent execution. This is the primary concern. The primary concern of concurrency control mechanisms in databases is that of maintaining the consistency of shared data access during concurrent execution, and we have discussed this issue in details. The second issue is attempting to have maximum possible concurrency without inconsistency. That is, instead of we can have concurrent execution by serializing everything, but that is not what we want. We want to achieve maximum concurrency because this provides maximum throughput. And in order to have these two, we try to do it in various ways. For this, we have mechanisms. There are several mechanisms. One of them is onus is on user. The system provides certain techniques which the user can use to write the transactions, and the onus is on the user to write consistent concurrent transactions. The second is system itself tries to detect possible inconsistency during concurrent execution and recovers from it or avoids it. It is not recovers from it, it is rather avoids it, which is a better term, because we are not discussing failure, we are not discussing system failure here. And among these two, we have already discussed the first type, where we discussed what are called lock based protocols. And among these lock based protocols, we discussed various types which are both trying to maintain consistency as well as having prevention of what are called deadlocks. When the system itself tries to detect possible inconsistency, it leads to several questions here. The first is, will the system try to analyze the actual behavior of each and every transaction. That is not possible. We are not discussing semantic analysis of transactions here. Therefore, the system abstracts each of these transactions into certain code based on which it tries to detect whether it is consistent or inconsistent. And in particular, the system removes all statements and retains only the read and write accesses to the disk. Based on these read and write accesses to the disk, the system tries to detect whether a possible inconsistency can occur. Based on this, we have discussed various issues, and one of them is the concept of serializability. That is, a concurrent schedule being equivalent to a serial schedule. That is, a concurrent schedule will execute concurrently, but its result will be equivalent to the execution of any one serial schedule. Among them, we have discussed two things. One of them is conflict serializability, and another is view serializability. And in conflict serializability, we saw that conflict serializability can be detected and tested very easily, whereas view serializability, though it encompasses cases of consistent behavior which a conflict serializable algorithm would detect as inconsistent, but still view serializability is often hard to detect. Based on among the log based protocols also, we saw techniques which try to maintain conflict serializability. Now we will see a mechanism by which the system itself tries to detect possible inconsistency during execution. The programmer does not have to write any lock or unlock. Transactions are just written by the programmer, and the system tries to detect when a schedule may become non-serializable. That is, when a schedule, and it will try to keep only those concurrent schedules which are by themselves only serializable. And among them, we will discuss today what are called time stamping protocols. So, the topic of this lecture will be time stamping protocols. Now, what are time stamped based protocols? In time stamped based protocols, the system, for every transaction which executes, the system gives a time stamp to that transaction. That is, it provides a set of timestamps, of which for every transaction Ti, a unique timestamp, any value, any integer value, denoted by Ts Ti. For a transaction, Ts is timestamp of Ti is provided to every transaction Ti. Now, what is Ts Ti? So, the first type of timestamp which we learn is Ts Ti. Whenever a transaction begins to execute, that is just prior to its execution, it is provided a timestamp. This timestamp may be a system related actual real time stamp, that is based on the system time, a time may be given, or it may just be a counter which when every transaction, when a particular transaction say T5 starts, that counter is 1. Then when T7 starts, the counter is 2. When T8 starts, the counter becomes 3. So, whenever one transaction starts, the counter is incremented by 1. It is just a logical timing value which indicates that this transaction started before or after another transaction. Therefore, if we have Ts Ti less than Ts Tj, we will know that in the system during execution Ti started before Tj. That is the concept of the timestamp Ts Ti. So, for every transaction we have a timestamp which indicates when this transaction started. Our timestamp based protocols will try to check whether the concurrent execution may become inconsistent or not, that is whether it will not be serializable. So, it will try to maintain whenever Ts Ti is greater than Ts Tj, whenever during a concurrent execution it will always try to ensure that the schedule is serializable to Ti followed by Tj. If TSTi is less than TSTj, then during concurrent execution, the schedule that occurs must be equivalent. It may not be a sequential schedule, but it may be a sequential schedule, that is fine, but otherwise it must be equivalent. At least very easily checking, what we will do is conflict equivalence. It must be conflict equivalent to Ti followed by Tj, to the serial schedule Ti followed by Tj. So that is what is the use of the first timestamp. Now for every shared data, we have got two timestamps. For every data item which will be shared, we have got two timestamps. One is called the W timestamp of that data item Q, or the write timestamp of that data item Q, and the other is the read timestamp or the R timestamp of the data item Q. So what is W timestamp Q? W timestamp Q denotes the largest TS value of any transaction that successfully executes write Q, and R timestamp Q denotes the largest TS value of any transaction that successfully executed read Q. Let us see the meaning of this. Suppose there is a data item Q and one transaction Ti whose TSTi, let us assume a logical time, whose TSTi is equal to 3, executes write Q. Let initially Q have no value, 0. Then we will have W timestamp Q will be equal to 3. After some time, if another transaction Tj with TSTi equal to 7 executes write Q, then this value will now become 7. By definition, if another transaction Tk whose TSTi value is equal to 4 executes write Q, then W timestamp Q will remain 7. Now whether we will allow this writing to be done or not is something which we will see later on, but the W timestamp will remain 7, even if this does first, this does a write, then this does a write, and then this does a write, then this by definition will remain 7. Similarly, R timestamp Q is the largest TS value of any transaction that successfully executes Q, read Q. Now let us see how we will utilize, what is our idea. The scheme of things is like this. Suppose a transaction Ti is executing. We will not bother about what it does with the other statements other than the read and the write statements. We are only bothered about the read and the write statements, and that too on those statements which are shared, which update shared data, which update its local and own data, which no other transaction will ever touch, is not checked by the system at all. Now whenever a read or a write is executed by transaction Ti, the concurrency controls mechanism immediately checks certain things. The first thing, whenever a transaction Ti starts, the concurrency control mechanism sets the new TSTi value, and it stores all the TSTi values and all the write timestamp and the W timestamp values of the required data. Now, whenever read and write is executed, before the execution of read and write, the transaction of any transaction Ti, the concurrency control mechanism does some analysis, and based on this analysis it tries to check whether there can be any inconsistency in the behavior, whether the equivalent whether the schedule which is now going on taking place is equivalent to the serial schedule, to a required serial schedule or not, and if it is not, some corrective action will take place. Now, let us see what will happen. So, let us see what analysis it does. That analysis is what is called the time stamping protocol. Now, suppose a transaction Ti issues a read queue. Now, the TSTI value will be compared with the W timestamp and the R timestamp of queue, because it has done a read queue which is shared. If it is not shared, then there is no problem, but if it is shared, then it checks. The first thing that it will check is whether if TSTI is less than W timestamp Q, then what does it mean? If TSTI is less than W timestamp Q, then what does it mean? It means that there is some transaction Tj which has written on the data item Q, and that transaction Tj started after transaction Ti. So, we have a possible situation here in which the transaction Ti started before transaction Tj, and it is going to write on the data item Q after a transaction Tj which started after Ti. Therefore, this schedule will never ever be equivalent, at least conflict equivalent, to the serial schedule Ti followed by Tj. So, if it is not going to be equivalent to the serial schedule at this point of time, the concurrency control protocol or the concurrency control mechanism will detect this by this condition, and it will reject the read. This read cannot be allowed because it is trying to read a data item which has been written by a transaction Tj, and Tj started after Ti, and this will, it may be consistent, but it will not be conflict serializable at all to Ti followed by Tj. So, Ti will be rejected, so this read will be rejected, but the question is how do we proceed with the transaction Ti? What we do is roll back Ti. Restart. So, Ti is rolled back and restarted. What happens if TSTI is greater than W timestamp Q? Then it is fine, because this transaction is going to read a data item which has been written by some other transaction Tj, and Tj must have, because W timestamp Q is the Ts of Tj. So, Ts of Tj means that Tj must have started before Ti. So, I am reading a data which is read by Ti. So, potentially there is no situation in which Ti cannot be conflict serializable to Tj, in the sense that Ti can follow Tj, at least based on this. Therefore, read is allowed. Equal to condition is not there actually. If we follow logical times, then equal to condition is not there. So I think it should be greater than. It is allowed. What about the case of TSTI and R timestamp queue? Suppose TSTI is less than R timestamp queue. It does not matter because both are reading. This has read and this has read. So there is no problem. Somebody has read, a transaction has read this before TI. Though TJ started after TI, TJ has read it before TI. But that is no problem because both have read it. If TJ would have written it, then that would be checked at that point of time. So neither is this a problem, nor is this a problem. I am sorry, this equal to may be there because TI itself may have written, but we are allowing only one read and then write. Therefore, this equal to makes no sense. Actually, equal to cannot occur because a transaction will normally read and then write. It will not write and then read. What is the use? If it itself has written, then why will it read again? So in these two situations, there is no problem. So here also read is allowed. So in read queue, we just disallow it at this time, we roll back T and restart it. When we restart it, it gets a new timestamp which is greater than the timestamp of TJ which has written. So there should be no problem. When you restart it, it will start again. This is the overhead. A partially executed schedule may have to be restarted. We next come to the write. Here again we see several cases. First is if TSTI is less than R timestamp queue, then TI started after TJ, which has, suppose TJ has written Q. If TJ has written Q, then we have TSTJ is greater than TSTI. So TJ started after TI, and TJ has read the value of Q. After that, TI is writing the value of Q, which means that this if we allow this writing to take place, then the transaction TI followed by TJ, this will never, the schedule that we will get will never be conflict equivalent to the serial schedule of TI followed by TJ. It may be conflict equivalent to the serial schedule of TJ followed by TI, but that is not the case. We already have our timestamp Q is equal to the TS of TJ, and which is greater than that of TS of TI. So if this is done by TJ, we have, if this is equal to TS of TJ, then we will never be, if we allow this right, we will never be able to have this schedule conflict equivalent to the serial schedule of TI followed by TJ. So in this situation, write is rejected. Let us come to the next situation. TSTI is less than W timestamp Q. In this situation, TSTI, so let this be TSTJ, let W timestamp q be the timestamp of a transaction Tj. If W timestamp q is equal to the time of transaction T, start time of transaction Tj, then Tj has started after Ti and Tj has written before Ti, will write. So, here again in the terms of conflict serializability we will not allow this, and we will say write is rejected and Ti rolled back. What are the other two situations that can occur in the otherwise part? One is TSTI is greater than R timestamp q, and the third is 3s Ti is greater than W timestamp q. These two situations are quite safe, because if that is this is of Tj, then TSTI is trying to write a data. Somebody has written this data, but whoever has written this data started before Ti. So, we can whoever has read this data has started before Ti. That is, the maximum person who has read this data has started before Ti. So, that is quite fine. Similarly, this is also quite fine. And we will note that since we have said this is the largest timestamp, this largest need not be very sacrosanct, because the protocol that we are following is such that whenever a person reads it, if it is less, we simply do not allow any reading to be done, any writing to be done. So, effectively only when it is larger we allow writing to be done, and whenever writing is done, the concurrency control mechanism updates the W timestamp, and whenever reading is done, concurrency control mechanism updates the R timestamp. It can be shown, and I think it is not difficult to show, that this timestamp based protocol is conflict serializable. That it is equivalent to some serial schedule. It is conflict equivalent to some serial schedule. And the second thing is, we can also easily show it is deadlock free. It is deadlock free because we are allowing rollback. Whenever we detect a mechanism, we are preempting something. We are taking something out of execution. If we have withheld it, then it would have reached to deadlock. But we are preempting it out and re-rolling it back and restarting it. But as you will see, like in the log based protocol, the overheads are of waiting and the onus is on the user. Here you have lot of additional overheads. The overheads are maintaining these timestamps, the read timestamp, the write timestamp, checking each time a read and write is executed. The system has to check, and the system has to update the read and write timestamps. So, there is lot of overhead, but the advantage is that the user need not bother at all about what is going on. And there may be chaining of the problem of these overheads, and the problem of time stamping is that you may have examples in which, since you allow everything to occur, you may have situations in which you continuously start rolling back this, that, and it would have been faster possibly to have executed it in a sequential fashion. Therefore, depending, if you know that such situations can continuously occur, then you can provide some checks, but otherwise time stamping protocol is one of the most widely used protocols in automated system automated protocols for concurrency control. But we must understand, we must look a little more deeper into this time stamping protocol and see if we can improve it. While improving it, see, our first criteria is that of maintaining the consistency of the system. If we maintain the consistency of the system, the next criteria is to try and see whether we can enhance the concurrency of the mechanism. And let us go back and see what we can do. Let us go back to our protocol. We had in read, if TSTI is less than W's times time, we have no other option, because it is trying to read a value which is written by a transaction which started after TI. That we just cannot allow, because if we allow this, then we can have thousands of examples in which this will lead to problems, because we are not analyzing what the code exactly is. The code may be no problem. The others are all allowed in the case of read. In the case of write, here also somebody has read it and we are trying to write after somebody who has started before me has read it. So this also we cannot allow, unless this we cannot allow if we want TI to be followed by TJ be the equivalent serial schedule. That cannot happen. But look at this. So this is a slightly more complex situation. TSTI is less than W times time. Okay. This means that this one has been written by a transaction TJ, and TJ started after TI. All right. Now TJ started after TI, and TJ has written now. I have to write this. Obviously, I cannot allow this to write after this, because it will never be conflict serializable. But the question is, do I have to roll back TI? Will it be sufficient for me to say that I will not execute the write statement, but I will continue with TI? Let us analyze the situation. TI has got write queue somewhere. TJ has got write queue somewhere. We want a conflict equivalent schedule in which this will write first and this will write second. That is, we want a schedule equivalent to a schedule in which this will write first and this will write second. Now, if it occurs that this will write first and this will write second, this write is useless, because this will be overwritten by this one. So if by chance TJ has written earlier, we will just say that TI need not write. We will just say TI need not write. The other situations in which TJ has written earlier and TI tries to read will be checked here. Will be checked here. If TJ has written and TI tries to read, will be checked here. Or TJ has read and TI tries to write, will be checked here. But if this is the only situation, then what we can say is that in TI we will not allow this write, but we will not roll back, we will just let it continue. So this is called a modification of the protocol. It's called Thomas's write rule. And it says that in this situation, the other situations are all identical. The other situations are all identical. It says in this situation, ignore write queue by TI. and let Ti continue. This way it prevents a rollback in a situation as late as possible. Maybe Ti will be rolled back because of some other reason, but at least for this reason it does not unnecessarily roll back Ti and therefore tries to reduce the amount of rollback. So, we have discussed another protocol, namely the time stamping protocol, in which it is the onus of the system to take care of how to maintain serializability or equivalent serializability and have as much concurrency as possible. We will see now in other schemes how we can organize the database in such a way that concurrency is maximized as far as possible. We will see that in the next lecture.